Okay, let's talk about the next topic, which is called improper integrals. What an improper integral is that it basically depends on what are the limits of integration. In other words, if we go from a to infinity, this is an improper integral. If we go from negative infinity to b, this is an improper integral. And if we go from negative infinity to infinity, this is also an improper integral. And in this video, we're only going to be looking at limits whose integrals whose limits go to infinity on one side or both sides. In the next video, we're going to look at improper integrals where the limits are just discontinuous at a point. So this is more towards infinite limits. So let's go through a quick definition of an improper integral with infinite limits. So I'm going to write it in blue. So this is the first part. So let's say we have a function that's defined continuously over this interval, right? And the reason why I'm defining it continuously over is that there's no breaks or any discontinuity. So the thing from a to infinity is continuous, so we can use this definition. So the the integral from a to infinity of f of x dx, the way we solve, or the way we have a solution with this, is actually we make a substitution. We make the top limit approach infinity. We can't necessarily keep it infinity throughout. We have to actually approach infinity. So that's what we're going to be doing. Similarly, if we go from negative infinity to b, if that's defined continuously on there, I'm going to scroll down. Oops, that's too much. There we go. We go the integral from negative infinity to b of f of x dx. And then the way we solve it very similarly. We substitute a as negative infinity and we take the limit approaching it, right? The final one is when there's continuous throughout the whole interval, or infinity to negative infinity to positive infinity. And I'm going to see if I can scroll out a little bit. There we go. Right there. What I want to do is find the integral from negative infinity to infinity of f of x dx. And we have to actually do something interesting here. And the way we do this is actually taking two limits. We want to take the limit as a approaches negative infinity from a to c, not b, of f of x dx, where c is just any point in between negative infinity to infinity. You can choose, actually, because we're just going to be using a integral property as b approaches infinity. So I broke it down into two parts, and this is fine because it's a property of integrals, basically saying if you have two integrals, you can break it as long as the connecting pieces are in fact connected. So a to c, c to b. So that means a to b is the same thing. So we're going to be looking at a few examples using one of these improper integral forms. Now that we know the definition of the improper integral with infinite limits, we are going to put it into practice. And the integral can be anything. It could be using integration by parts, so substitution, partial fractions. You can even find the volume of the volume of a solid of revolution using infinite limits, and we just basically attack it the same way. So the way we attack this problem is by substituting b. I want to find b such that when we approach it to infinity, this is the same thing. And now we can actually evaluate this integral in terms of the 1 and the b, right? So the way we do this is integration by parts. I'm going to use tabular methods. So like this. So we have x and then the other function here. I just keep differentiating x, so I get 1 and 0, and I keep integrating e to the negative x. And then we just simply, this is plus and minus. So we just basically multiply across, and what do we get? We get negative x e. Let me actually write the limit in first. limit as b approaches infinity of negative x e to the negative x minus e to the negative x evaluated at b and 1, right? So whatever b is and then 1. And then we can just plug it in. Do we want to keep this limit? Because I'm not evaluating the limit yet. I just said I'm going to evaluate the integral, in fact. So b e to the negative b minus e to the negative b. That whole thing minus this whole thing, which is 1 e to the negative 1 minus e negative 1. I guess from here I can do a little bit of simplification. The limit as b approaches infinity of, I guess, negative b over e to the b minus 1 over e to the b from that, and then we subtract, so it basically distributes a negative, and then we can combine these because these are kind of like terms, so this would be plus 2 over e to the first. That's what this sums up to be. Now we can actually evaluate this limit, and we can actually use skills we learned from L'Hopital's rule, and all we have to basically know is that this first term is an indeterminate form, infinity over infinity, so we take the derivative, and then the b goes to 1, and e to the b goes to e to the b, right? So it's going to approach 0. So I can safely say that the first term is 0, and same with the second term is 0, and then we're left with 2 divided by e. That means this whole limit is 2 over e. So this is the general process, right? We have to solve the problem by kind of substituting b as the upper limit. And we take the limit, and then we just go through the regular process, and then we just have to evaluate the limit as b approaches infinity, and we basically arrive at our answer. So now we can go to our next example. Okay, so now we have this integral, the integral from negative infinity to infinity of 1 over the quantity 1 plus x squared dx. And notice that the limits that go to infinity actually appear on the lower and the upper limits. So we have to actually take it into two parts. The limit as a approaches negative infinity of a, and I can choose any point. And for the purpose of this, usually you like to choose 0. You also like to choose, maybe 1 might be a good answer or a good choice. 0 because I already know the integral is arctangent, and I know exact values of arctangent of 0 and not really like 3 and 2 or negative stuff. So that's why I'm going to choose 0. And then we use the same function, 1 plus x squared, oops, there's already dx. And then we want to do the other part as b approaches infinity of, 0, right? It needs to connect the pieces together. And we use the same function. So now we can continue here. I already know the integral is arctangent, so the limit as a approaches negative infinity of arctangent of x evaluated these two, and then plus the limit as b approaches infinity of arctangent from these two values, and I can actually just plug it in or evaluate these limits straight. So arctan of 0 minus arctan of a plus arctan of b minus arctan of 0, and hopefully you know what these arctan values are. You can use your calculator if they allow a calculator. So arctangent of 0 is simply 0, so these two go to 0. And then what are we left with? We are left with arctan of negative infinity, that is negative pi over 2, so it's negative pi over 2. And then plus arctan of infinity is pi over 2. If you don't know that, I guess take a look at a unit circle. The way I think about tangent values, actually, if given this is a unit circle, is actually thinking about this line that I drew right here as a slope, right? Because it's sine, so sine here divided by cosine is kind of like rise over run. So that's how I think of it. So as we keep going this way, it's going to approach infinity. In other words, the slope is infinity, or it's just pi over 2 radians. And same thing here, it's approaching negative infinity, so it's negative pi over 2. That's how I like to think of arctan and tangent. So if you want to take that for yourself, you can. So then we just evaluate this, and this is just pi over 2 pi over 2, which is equal to pi. So that's the area under the curve of the arctangent, I mean not of the arctangent function, of the function 1 over 1 plus x squared from negative infinity to infinity. And we just found it to be pi. And usually these are kind of weird because out of just a simple rational function, if you take the area under a curve, you just get pi, which is kind of interesting to me because rational functions and trigonometry can only, I guess, be related if you do some calculus to it, which is interesting. Let's do one more example. I guess the final example is actually going to be a really, really easy one, but it makes an important point that I want to make. It's the integral of, as from 1 to infinity, of simply just dx over x. And we already know how to solve these types of problems. The limit as b, you can use any letter for this. I like to use b as the upper one and a as the bottom one. But you can use any letter if you want. If you want to use the same letter to stay consistent, it doesn't matter. I just like using b because it's the upper limit, which is equal to the limit as b approaches infinity of the natural log of x evaluated at these 2 points. In other words, it's the limit, so I'm going to evaluate the limits of integration. It's ln b, ln b minus ln 1. So ln 1 is 0, so we basically have the limit as b approaches infinity of the natural log of b. And this can be the case in many improper integrals, where when we evaluate this limit, notice that the ln function, if you evaluate it, goes off to infinity. Notice that we can actually have infinite, I guess, area under a curve because of this infinite bound or infinite limit. We actually give these a special name. If they go to infinity or negative infinity, we say they diverge, or the improper integral or the integral itself diverges. Otherwise, if a number, like the other examples, let me just scroll up here, like the arctangent example, it goes to pi. It converges to pi is what we call it. So there's kind of two possibilities people like to answer, especially with improper intervals. Does it diverge or does it converge? Right? Converge just means a number. It could be any number. Diverge means either infinity or negative infinity. And that's the point I want to make, that we can have diverging integrals. So that's it for this video. In the next one we'll talk about improper integrals with discontinuities within that and how to approach those using improper integrals. So that's it.